This video begins the Exploiting Linux Vulnerabilities section with redirecting execution. We'll create a vulnerable program in C, view memory usage with GDB for normal execution of the program, and then perform a buffer overflow exploit to make an unexpected result. Here's a simple program that calls a test PW subroutine, which reads a password from the user and does some bit flipping operations to decide whether to return 0 and say the password was correct, or return 1 and say the password was not correct. The password is read from the user with the getS routine and put into a variable that only has room for 10 bytes. So if you put in more than 10 bytes, you can overflow this and take over control of the machine. We'll disable address space layout randomization so the code stays in a predictable memory location to make the attack easier, and compile it with a few compiler options: -G to include symbols and connect it to the source code, -static to include libraries natively, and -NoPy to avoid producing position-independent executables. This is an old-fashioned way to compile code, and it makes the attack simpler. So normal execution of the program, it asks you for a password, and if you get it wrong, you see fail. But if you put in a long password, you see the segmentation fault message, indicating that you have somehow used memory beyond the available memory to a routine, and that indicates the presence of a vulnerability. So let's go that far. Here we have control of our Kali Linux machine through SSH. And so first I remove address space layout randomization, and now I take a look at my code, which is here. Let's get rid of the colors. And here's the routine that contains the overflow. Here's the variable with 10 characters, and here it reads a password from the user without limiting it to 10 characters. So if you overflow all the local storage for this routine and overwrite the return pointer, when it executes these return statements trying to get back to the main routine, it will instead be redirected wherever I tell it to go. So let's compile it. Here with those switches, you get a couple of warnings, but you don't get any error messages, so it'll work. And if you run the program with a short password, you get fail. But if you run it with a long password, you get segmentation fault. So that is a vulnerability. And it's not always exploitable, but this vulnerability is exploitable. If you use GDB to view it in a debugger, I use the -Q switch just to avoid having a large banner printed, and you can list the source code with the list command and see it in C. You do not need to directly refer to assembly code at this point. We can find the vulnerable command, which is line number 8, and put a breakpoint at that line and somewhere after it. So we can examine the condition of memory before and after the overflow. So if you run, the program will proceed to the breakpoint. If you do info registers, you will see the registers in the processor, and the ones important to us are the ESP and the EBP. This is the beginning of the stack frame and the end of the stack frame, which at this point, when I ran it for making these slides, went from 610 to 638. If you execute the overflow by continuing and putting in a long password, and then examine memory with x/20x ESP, you will see 20 hexadecimal words starting at the stack pointer, and you can highlight the stack frame here going to EBP, the 32-bit words starting at address 638. So the highlighted region contains the injected code. Here's AA, BB, and so on. AA is actually up here. 41, 42 is B, 43 is C. And here's the stored instruction pointer, which has been overwritten by 50 and 51. So those are letters I control, so I can control the extended instruction pointer by replacing the PP and QQ in that injection string with the address of code to execute. Now all I have to do is choose an address. To find an address, I disassemble main, and even though the assembly code may be a little difficult to read, you can just look at the right side and read the names of the routines. This calls the test PW subroutine. Here's a puts, and here's another puts. And I know from the pattern of the C source code that the first one prints fail, and the second one prints "you win." So to print the "you win" message, I want to go to this address, which will push the pointer to the "you win" message on the stack, and then call puts to print it. So it's this address, 080488ED. I can make Python code to print that out. You see it here, AABBCC up to the 00, and instead of PPQQ, I put that address bytewise backwards. And now, run that exploit code and put it in a text file called attack-pwd. I can run with --args less than attack-pwd in GDB to feed in that attack code, and it will run to my breakpoint and let me examine the condition of the stack. Now it has letters I injected and then the address I injected. And when I continue execution, I'll see the "you win" message. After that, the program crashes because I haven't been very careful at preserving the memory conditions and some of the other registers are fouled up. But I do get to the "you win" message, and if I run this outside the debugger, in the normal shell, I also win. So let's do that. If I go here and run the program in GDB, I can now list the contents of memory, or list the source code, and I will see gets here. So I'm going to put a break at line 8 and a break after line 8, which could be in any of several places. I'll just put it at line 9. So now if I run the code, it will reach the breakpoint, and I can do info registers, which I can abbreviate to IR, and I will see ESP and EBP. So this stack frame goes from address 600 to an address ending in 628. So look at the condition of the stack. I can do X20X, ESP, and a highlight from 600 to the word. This is the word starting at 620. This one starts at 624, and this one starts at 628. So that is the stack frame reserved for local storage in the test_PW routine, and this is the extended instruction pointer. That is my target. So if I continue execution with a C, I can now put in my attack string. All right, that might do it. Let's inject that, and now examine the registers again. Or rather, just the stack frame, because I know the registers, and I know it goes here to 628. So again, I made it so the 51 and 50, which is the end of my attack string, is the text that ends up in the extended instruction pointer. So I'm going to put this in the clipboard. I can now make my attack. The only thing I don't have is an address to target, so let's disassemble main. And here's the first puts, and there's the second puts. So this is my target address, 080488ED. So I'm going to quit here, and quit here, and then make an attack file. And I think I have one ready to go here. Let me nano attack. All right. That's the text string, but I want the exploit file that creates it. All right. There. Let me get rid of the colors. All right. And I used sys standard out right just to get rid of the carriage return at the end, which may not be necessary for this exploit, but it doesn't hurt. Here I put the address 080488ED. I'm going to leave and check that. 88ED. And if I scroll up here, here's the second puts. It is 88ED. So that file should work. So if I run that file, exploit, it prints out the text here, and the last few bytes are unprintable. But I put that in a file called, say, A. And now if I run that in GDB, I run the password file, and I run it with --args less than A. It runs down and it prints the "you win" message and then gives me a seg fault, so it's working. The fact that an exploit works inside the debugger does not always mean it will work outside the debugger. So it's worth testing here too. If I put in that input from A, it's /pwd, there we go. Again, I get the uwin, and the segmentation fault. So this exploit is working. It's a little sloppy because it crashes the program, but it still demonstrates the important point: we can take over control of the machine with a buffer overflow exploit.